Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about elastic critical moment NCR for a fixed ended beam. So let's look at what we have discussed so far. So far, we have found out the N0 critical, which is equal to pi by L the whole square into EIY into root of IW by IY plus GJL square divided by pi square EIY, which is based on the following assumptions. Equal end applied at centroidal axis of the member. The beam is simply supported at the ends, which means that twisting is prevented at supports. The lateral bending or warping is allowed. Third, the member is prismatic and it is doubly symmetric cross-section. But in practice, beams vary from the basic case. Different types of loading, whereas unequal moments take place. Single curvature as well as double curvature. We have a concentrated load. We can also have a uniformly distributed load. The loading condition can be the load applied at the shear center, which is a normal condition, and we can also have a load applied at the top as well as the load applied at the bottom of the flange. Now let's look at the bending moment diagram for each one of these cases. As you can see, there is a uniform bending moment diagram, there is a linearly varying bending moment diagram, so on and so forth. And the corresponding differential equation, which is a homogeneous linear ordinary differential equation with constant coefficient, is given on the right hand side, where m0 is a constant value. We have solved the differential equations to find out the value, which is m0 critical equal to pi by L the whole square into EIY into root of IW by IY plus GJL square divided by pi square EIY. Whereas for other loading cases, it is a homogeneous linear ordinary differential equation with variable loads. By variable loads, the load is variable along the length of the member Z. This can be solved using energy method. So the total energy of the beam is pi equal to U plus V. Here MCR is obtained using the energy method pi equal to U plus V, where here U is the strain energy of the beam. Here the potential energy V varies according to the loading type, as you can see here. For three different loading cases, we have three different potential energy equations. However, the strain energy given in the right hand side does not change with regard to the loading condition, it remains the same. Now let us look at the elastic critical moment here. So the elastic critical moment is given for uniform loading case as we have described above. For other loading conditions, we have MCR equal to C sub B into M0 critical, where C sub B is the lateral torsional buckling modification factor. And this value is given as 0.282 minus 0.436 psi plus 0.282 psi square the whole power minus 1 by 2. This is derived based on the approximations. Whereas the C sub B given by EISC is 1.75 plus 1.05 psi plus 0.3 psi square, which should be less than or equal to 2.3. This was in the code from 1961 till 1986 of EISC. Here psi is given as M minimum by M maximum. For a point load case, the C sub B is given as 1.37. And this is all based on the assumption that the load is acting through the shear center, which we have derived. What about if the load is acting away from the shear center, either at the top of the flange or at the bottom of the flange? So the lateral torsional buckling modification factor, C sub B, can be modified into three different ways, depending upon the loading condition. For load at the bottom flange, C sub B is given as AB. And for load at the shear center, C sub B is given as A, and for load at top flange, C sub B is given as A by B. Now, A is defined as 1.35 and B equal to 1 minus 1.779 divided by R square plus 2.039 divided by R, which is for a concentrated load at midspan. Here, R square is defined as L square GJ by EIW. For a uniformly distributed load, again A is given as 1.12, B equal to 1 minus 1.522 divided by R square plus 1.681 divided by R. All these above equations are based on the research work carried out by Nethercott and Kirby, published in AISC Engineering Journal in the July of 1971. A similar version of this can also be obtained from the textbook Structural Stability, Theory and Implementation by Chen and Louis. The previous equations leads to unconservative values of C sub B for non-linear moment diagrams. The general and practical conditions dictates non-uniform bending moment diagram as shown here. So the lateral torsional buckling modification factor is given as C sub B equal to 12.5 M max divided by 2.5 M max plus 3 MA plus 4 MB plus 3 MC, where MA, MB, MC are basically quarter, half and 3/4 point along the length of the beam. And this is the same equation that is also present in AISC 360 as you can see from the right hand side. However, it should be noted that the beam is assumed to be torsionally restrained at the supports, that is restrained against twist, which is gamma of the cross section, and rotation along longitudinal axis alone, which means that there is no twisting that is taking place in the length of the beam. The beam is free to warp, which means that there is no warping restraint provided at the supports. So it is basically a simply supported beam. So some of the limitations of the previously derived equations are: the lateral torsional buckling modification factor C sub B accounts for changes in loading type and loading conditions alone, which we have already derived, as you can see here. But what if the beam is not simply supported at the ends, if it has a different boundary condition? So in practice, beams possess various support conditions due to connections. So this shows the top view or the plan view of the beam, and we have three different conditions. One is for lateral bending, another is for twisting, and another is for warping. This boundary condition does not allow lateral bending, as you can see here. It does not allow twisting, but it allows warping, which means that the beam can axially deform, in the plane of the cross section. And for this boundary condition, which is fixed to a plate here, lateral bending is allowed, twisting is not allowed, and warping is also not allowed because it is welded to a steel plate, as you can see here. The third boundary condition is such that lateral bending is not allowed, twisting is also not allowed, and warping is also not allowed. In such situation, it is a fully fixed condition. Now let us find out the solution for MCR of a fixed beam subjected to equal end moments. So this is a fixed ended beam with length L, and you have moments M0 and M0 acting in this direction. So equally applied end moments of equal magnitude at shear center, which is going to produce a smiley curve or a single curvature. And this is the loading condition here. It is applied to an I section where the IXX is very much greater than IYY. Establishing the potential energy, pi of the beam is given here. As usual, we omit the term V, which is very much less than U and gamma. So the total potential energy of beam is as given in the slide here. So the approximations are based on U equal to A into 1 minus cos 2 pi z by L and gamma equal to B into 1 minus cos 2 pi z by L. Here these approximations are trigonometric approximations chosen such that the boundary conditions will be satisfied for a fixed end beam. Now let us check if these approximations satisfy the boundary conditions. Assume ends of the members are laterally restrained, which is U equal to 0. Bending about minor axis is restrained, which is U double dash is not equal to 0. Restrained against twist, which is gamma equal to 0. And warping is restrained, which is gamma double dash not equal to 0. So now let us look at the first boundary condition, which is laterally restrained, which means that U should be equal to 0. So U equal to A into 1 minus cos 2 pi z by L. So when we substitute U at z equal to 0, we have A into 1 minus cos 0, which is cos 0 becomes 1. So A into 1 minus 1 becomes 0. So U at z equal to 0 is 0. Now at U equal to z equal to L, which is A into 1 minus cos 2 pi L by L, which means that 1 minus cos 2 pi, again cos 2 pi is equal to 1. So which becomes A into 1 minus 1, which again becomes 0. Now let us look at the second boundary condition, which is bending about minor axis is restrained, which is U double dash should not be equal to 0. So we take the derivatives U dash equal to A into 2 pi by L into sin 2 pi z by L, U double dash equal to A into 2 pi by L the whole square into cos 2 pi z by L, and gamma dash equal to B into 2 pi by L into sin 2 pi z by L, and gamma double dash equal to B into 2 pi by L the whole square into cos 2 pi z by L. So let's take U double dash. So U double dash is A into 2 pi by L the whole square into cos 2 pi z by L. U double dash at z equal to 0 equal to A into 2 pi by L the whole square into cos 0, which is equal to A into 2 pi by L the whole square, which is not equal to 0. Now U double dash at z equal to L equal to A into 2 pi by L the whole square into cos 2 pi L by L, which also becomes A into 2 pi by L the whole square, which is not equal to 0. Now let's look at the third boundary condition, which is restrained against twist, which is gamma equal to 0. So gamma equal to B into 1 minus cos 2 pi z by L. Gamma at B equal to 0 equal to B into 1 minus cos 0, which means that B into 1 minus 1, which is also equal to 0. And gamma at z equal to L equal to B into 1 minus cos 2 pi L by L, which is also equal to B into 1 minus 1, which is equal to 0. Now the third boundary condition is also satisfied. Now let's look at the fourth boundary condition, which is warping is restrained, which is gamma double dash not equal to 0. So when we substitute gamma double dash at z equal to 0, it is b into 2 pi by L the whole square into cos 2 pi into 0 by L, which is equal to b into 2 pi by L the whole square, which is not equal to 0. Similarly, gamma double dash at z equal to L equal to b into 2 pi by L the whole square into cos 2 pi L by L, which is equal to again b into 2 pi by L the whole square, which is not equal to 0. Now the boundary conditions are satisfied, which is u at z equal to 0 comma L equal to 0, u double dash at z equal to 0 comma L is not equal to 0. Gamma at z equal to 0 comma L is equal to 0 and gamma double dash at z equal to 0 comma L not equal to 0. Now let us substitute the approximations into the total potential energy equation of the beam pi. So when we do so, we get a lengthy equation here. We have 4 terms, 1, 2, 3 and 4. We can solve each one of those terms individually and we can sum it up. So solving part 1 is 0 to L half into EIY into d square u by dc square the whole square. So when we substitute that, d square u by dc square, we have half into EIY into 0 to L a into 2 pi by L the whole square into cos 2 pi z by L the whole square. So again we can simplify this further and we can substitute the value of L by 2 for 0 to L cos square 2 pi z by L. Now we can also use the integrals on the right hand side, which is 0 to L cos square pi z by L into dz is equal to L by 2. So when we substitute that, we can further simplify this equation as given here, which becomes equation 1, which is EIY into a square into 4 pi power 4 divided by L cube, equation 1. Now let's solve equation 2. We can substitute the value of d gamma by dc in this equation 0 to L half into gj into d gamma by dc the whole square dz. So when we substitute that and we square that, again we can take advantage of the equations given on the right hand side, which is 0 to L sin square 2 pi z by L is equal to L by 2. So when we substitute that, we get a simplified equation gj b square into pi square by L, which is equation 2. Now let's look at equation 3, which is 0 to L half into EIW into d square gamma by dc square the whole square into dz. So when we substitute these values, we can simplify this further. Again, taking advantage of the formulas given on the right hand side, which is 0 to L cos square 2 pi z by L equal to L by 2. We have this simplified equation, which is EIW into b square into 4 pi power 4 by L cube, which is equation 3. Now solving part 4, which is minus mx into 0 to L du by dz into d gamma by dz into dz. So when we substitute the values here, we can simplify this further. Again, taking advantage of the equation 0 to L sin square 2 pi z by L is equal to L by 2. We get the value minus AB m naught into 2 pi by L the whole square into L by 2. So on further simplification, we have minus AB m naught into 2 pi square by L, which is equation 4. Now let's substitute 1, 2, 3 and 4 in the above pi equation. We have this big equation as you see on the screen. This is the total potential energy equation of the beam. Using the principle of stationary total potential energy, for equilibrium, the total potential energy of the system pi should be equal to 0, which means that del pi is equal to 0. The critical moment is reached when the neutral equilibrium is possible. So the requirement for neutral equilibrium is such that the partial derivative of pi with respect to A and B should vanish. Now applying partial derivative of pi with respect to A, we get the above equation dou pi by dou A is given here. One more time, when we simplify that, we get the equation 5, which is 8 into EIY into pi power 4 divided by L cube into A minus m naught into 2 pi square by L into B. Similarly, applying partial derivative of pi with respect to B, we have this equation here. We simplify this further and we can call it as equation 6, which is 2 gj pi square by L plus 8 pi power 4 EIW by L cube into B minus m naught into 2 pi square by L into A, which is equal to 0. So when we arrange the equations 5 and 6 in the form of a matrix, we have this equation as shown here. Now for non-trivial solution, the determinant of this matrix should be equal to 0. So we find out the determinant of the matrix here and we simplify this determinant of the matrix as you can see from the equations here. We can simplify this further. It's simply algebraic simplification. So when we simplify this further, we have 2 EIY divided by L into 2 GJ pi square by L plus 8 EIW pi power 4 by L cube is equal to m naught square critical. So we multiply and divide with 2 pi square by L on the left hand side We further simplify this and we get the value 4 pi square EIY divided by L square into GJ plus 4 EIW pi square by L square equal to N naught square. We can represent the above equation as L by 2, which gives rise to the equation pi square EIY divided by L by 2 the whole square into GJ plus EIW into pi square divided by L by 2 the whole square bracket close is equal to N naught square critical. So applying square root on both sides, we have M naught critical equal to pi square EIY divided by L by 2 the whole square into GJ plus EIW into pi square divided by L by 2 the whole square. So this is the elastic critical buckling moment for a beam whose ends are fixed and is subjected to equal end moments. So the elastic critical moment M critical for beams for a fixed end beam subjected to equal end moments is given by the equation on the left hand side. And for a simply supported beam subjected to equal end moments, we have the equation on the right hand side. Both these equations are same, except on the fixed end beam we have L by 2, whereas on the simply supported beam we have L. Now this can be represented L sub LT, which is the effective length against lateral torsional buckling. So we have a generic equation which is M naught critical equal to root of pi square EIY divided by LLT the whole square into GJ plus EIW into pi square by LLT the whole square. So this LLT is equal to 1.0 for simply supported beams and it is equal to 0.5 for fixed end beams. Now the question is, how do we select L sub LT from IS 800? So Annexure E, page number 128 of IS 800 gives the equation on the left hand side, which is basically the L sub LT equation for M critical for different types of boundary conditions. And table 15 in the main body of IS 800 gives you the L sub LT, which is a function of restraint at the supports as well as the loading condition. For simply supported beams, the effective length L sub LT is classified based on conditions of restraint at the supports, which is shown above. Similarly, for loading conditions, which is also shown above on the right hand side. Now let us look at the condition of restraint at the supports. As you can see here in the notes, we have 2 points highlighted. The first point is that it is a torsional restraint, which means that it prevents rotation above the longitudinal axis gamma. The second one is the warping restraint, which prevents rotation of the flange in its plane, which is gamma double dash. So the various conditions of restraint at the support can be highlighted here. So let us revisit the support conditions. We have lateral bending, twisting and warping. What is shown here is the plan view of the beam. So we have lateral bending arrested due to this boundary condition. We have twisting also arrested and we have warping allowed. So the lateral bending is arrested and it gives indication that U double dash is not equal to 0, which is the lateral bending moment is not equal to 0. The twisting gamma equal to 0 and warping gamma double dash is equal to 0. Now for the second boundary condition, we have lateral bending allowed, which is U double dash is equal to 0 and twisting not allowed, which means that gamma equal to 0 and warping not allowed, which means that gamma double dash not equal to 0. Now the third boundary condition is it is fully fixed, which is lateral bending not allowed, which means that U double dash not equal to 0, twisting not allowed, which is gamma equal to 0 and warping not allowed, which means that gamma double dash not equal to 0. Now let's look at the loading condition. So there are various loading conditions here. The load can be applied at the shear center. This is a normal condition. The load can be applied at the top of the flange as well as the loading can be applied at the bottom of the flange. Now let us understand how the derived equation compared with the provisions given in IS 800. So this is table 15, which contains two types of supports. The first support is torsional restraint. The second support is warping restraint. The loading condition is normal as well as destabilizing. And M naught critical is given as pi square EIY divided by L sub LT the whole square into GJ plus EIW pi square divided by L sub LT the whole square. All of them under the square root. Here L sub LT equal to 1.0 for simply supported conditions. And the L sub LT is equal to 0.5 L for fully fixed conditions. The support conditions are highlighted in the figure below. For simply supported condition, we have restraint against twist gamma equal to 0. So this means that it is fully restrained against twist. So we look at the fully restrained condition, which is number 5 in the boundary conditions as per the table 15 of IS 800. And the next boundary condition is that it is free to warp, which is gamma double dash is equal to 0, which indicates that warping not restrained in both the flanges. The value for L sub LT is given as 1.0 for normal condition. The boundary condition C indicates that it is restrained against twist, which is gamma equal to 0, So, which belongs to the number 1 boundary condition in table 15, which is fully restrained. Now, let's look at the boundary condition D, which is warping is restrained, gamma not equal to 0. As you can see here, both flanges are fully restrained. The value is given as 0.7. Here we can see that 0.7 is the codal provision, whereas the theoretical derivation is given as 0.5 L. It is bound to have a difference between the theoretical derivation and the practical scenario, simply because the boundary conditions that are assumed in the theoretical derivation will not be actually reflected in the practice. A similar deviation can also be observed in columns where for fixed end columns the K factor is 0.5, and as per IS 800 it is given as 0.65. So, there is a close to a 20% increase in the effective length factor. Similar situation is reflected here, as you can see here. So, the L sub LT equal to 0.5 L is based on theory, whereas the practice indicates that it should be 0.7 L. However, it should be noted that the beam is loaded with equal end moments at shear center in both the cases. The limitations of the previously derived solutions are given here. The first one is that equal end moment is applied at the central axis of the member. This is handled by the lateral torsional buckling modification factor C sub B, which accounts for the changes in loading type and loading conditions alone. The next one is that the effective length against lateral torsional buckling L sub LT in IS 800 accounts for both different types of loading conditions plus different types of support conditions. Now, let's focus on the third one, which is the prismatic member and doubly symmetric cross section. In steel structures, we not only have doubly symmetric cross sections, but we can also use singly symmetric cross sections, as you can see here. So, these are the two sections that are commonly used in steel structures. Both of them are singly symmetric cross sections. The first one is an I section where the top flange is actually higher width than the bottom flange, and the next one is a channel sections. Here you can see that the shear center and the centroid do not coincide. So, upon application of load, the eccentricity between the shear center and the centroid amplifies the displacements u, v and gamma. However, the previously derived equation of M critical does not account for this eccentricity. How do we ensure that M critical accounts for different types of cross sections with eccentricity between shear center and centroid? So, now let's look at both the cross sections here. Both of them are bending about major axis, which is x-axis, as you can see here, but there is a difference. The difference is that the first cross section, which is the I section, is symmetric about minor axis, which is y-axis, whereas the next one, channel section, is symmetric about a major axis, x-axis. Upon the two cross sections, the channel cross section needs to be referred to a specialized literature to obtain M critical. However, let us see how we can derive M critical for monosymmetric I sections shown here. Let's look at the simply supported beam with MA acting on one side and M sub B acting on the other side, which is equal to psi into MA, where psi equal to MB by MA, and MB is the minimum end moment and MA is the maximum end moment. Now, for doubly symmetric cross sections, so using energy method, we have derived the following terms. The first three terms correspond to the strain energy, which is based on the three displacement components. The third term is based on the potential energy of the beam due to unequal end moments. Now, we have the term MCR equal to C sub B into pi square EIY divided by L square into root of IW by IY plus GJ into L square by pi square EIY. This is the corresponding M critical for the equation above, where CB is based on the approximations we have derived previously, which is equal to 0.282 minus 0.436 psi plus 0.282 psi square, the whole power minus half. And using AISC, we have CB equal to 1.75 plus 1.05 psi plus 0.3 psi square for moment diagrams with linear straight lines. And for non-linear moment diagrams, we have CB equal to 12.5 mx divided by 2.5 mx plus 3 ma plus 4 mb plus 3 mc. Here we have a similar M critical equation for a fixed end support conditions. The only change here is that here L is replaced by L by 2. So, this is based on equal end moments. The equation on the top is a generic equation for unequal end moments. However, in order to solve for equal end moments, the potential energy has to be changed as we have done here. And then the C sub value corresponding to equal end moments now becomes 1.0. And for fixed condition at both ends of the beam, the L becomes L sub 2. Basically, the lateral bending U double dash not equal to 0, twist about longitudinal axis gamma equal to 0, and warping, which is gamma double dash not equal to 0. So, this can be written in a generic form which is MCR equal to pi square EIY divided by L sub LT the whole square into root of IW by IY plus GJ into L sub LT the whole square divided by pi square EIY. So this L sub LT is the effective length against lateral torsional buckling, which is also known as LTB. So the generic equation IS 800-2007 accounts for different types of loading conditions plus different types of support conditions. The next challenge is, how do we account for singly symmetric cross sections where the shear center and the centroid do not coincide? In such situations, upon application of loads, the eccentricity between the shear center and the centroid amplifies the displacements u, v and gamma. To solve this problem, Clark and Hill has derived a new pi equation, as you can see here. It is very similar to the old equation, except that there are two additional terms that have been taken into consideration. The additional terms are integral of 0 to L k into m into gamma dash square into dz plus half into integral of 0 to L pg gamma square into dz. The last two terms takes care of the potential energy of the beam due to eccentricity between the shear center and the centroid. Here, G is the distance from shear center to point of application of transverse load, positive when the load is below shear center, otherwise negative. P is transverse load on a unit length of beam, and K is given as E plus 0.5 integral of A into x square plus y square into YdA divided by I sub x. Now substituting capital Z equal to small z by L and capital M equal to capital M bar into small m. Basically, we are non-dimensionalizing the parameters, and here M is the bending moment diagram at any point in a beam. M bar is the maximum value of bending moment in the beam as a function of Z, and M is a function of Z. So when we apply del pi is equal to 0, we have this equation as shown below here. And when we assume certain functions C1, C2 and C3, we can simplify this equation much further, as you can see from here. We are also considering approximations for the term U, gamma and M and solving for M bar equal to M critical. We have the simplified form of M critical equal to C1 into pi square EIY divided by KL the whole square into C2G plus C3K plus root of C2G plus C3K the whole square plus IW by IG into 1 plus GJKL whole square divided by pi square EIW bracket close. So this is a generic equation for sections symmetric only about minor axis, as you can see here. And this is based on the work carried out by Clark and Hill and was published in the Journal of Structural Division, Proceedings of AACE, July of 1960. The title of the paper is Lateral Buckling of Beams. Now, this is not exactly what is given in IS 800. The IS 800 has a slightly different form, which is given here, which is M critical equal to C1 into pi square EIY divided by L sub LT the whole square into K by K sub W the whole square into IW by IY plus GIT into L sub LT the whole square divided by pi square EIY plus C2 y sub G minus C3 y sub J the whole square power 0.5 minus C2 y sub G minus C3 y sub G bracket close. This is given in page 128 of Annexure E of IS 800-2007. Now, where y sub G equal to y sub S minus 0.5 integral of A into Z square minus Y square into YdA by I sub Z, where y sub G is the distance between the point of application of the load and the shear center of the cross section and is positive when the load is acting towards the shear center from the point of application. L sub LT is the effective length of the beam against lateral torsional buckling, and K is the effective length factor of the unsupported length accounting for boundary conditions at the end lateral supports, analogous to effective length factors for compression members with end rotational restraint, which is equal to 0.5 for complete restraint against rotation about weak axis, 0.7 for case of one end fixed and other end free, and 1.0 for no restraint, that is free to rotate about its weak axis. Now here K sub W is the warping restraint factor. Unless special provisions to restrain warping of the cross section at the end lateral supports are made, K sub W should be taken as 1.0. So now this equation shown above, which is a generic equation present in IS 800, takes care of different types of loading conditions, plus different types of support conditions, plus different types of cross sections. How does it take into account? Which is given in page number 129 of Annexure E. So as you can see here, table 42 gives the constants C1, C2 and C3 for different types of loading conditions as well as different boundary conditions here. The loading conditions are dictated by the psi values and the support conditions are given for various values of K. The different constants C1, C2 and C3 are also given in the last three columns. This entire table 42 is present in page number 129 of Annexure E of IS 800. So this table is a lengthy table, and you can see that different boundary conditions and loading conditions are also given here. Again, this is for loading conditions where uniformly applied load as well as point loads are given for different boundary conditions as well. So now let's look at the comparison between columns and beams. So the effective length of columns, as you can see here, 4 different boundary conditions and 4 different bucking modes for columns are given here. General equation for critical Euler buckling load is P critical equal to pi square E divided by KL the whole square. And K varies depending on the boundary conditions 0.5, 0.7, 1.0 and K equal to 2.0. And here the K value is a function of support conditions only. Table 11, page number 45 of IS 800 gives the different values of K depending upon the boundary conditions. Now let's look at the effective length of beams. In practice, beams are subjected to transverse loads, as you can see here, as well as different loading conditions, whether the load is applied at the shear center, above the shear center or below the shear center, and different support conditions due to connections, as you can see here. What you see here is the generic equation for M critical, which is pi divided by L by L sub T the whole square into EIY into root of IW by IY plus DJ into L sub LT the whole square divided by pi square EIY. Unlike axially loaded columns, the effective length of a beam against lateral torsional buckling is a function of restraint conditions or support conditions and the loading conditions. Table 15 gives the effective length for simply supported beams L sub LT, and table 16 gives the effective length L sub LT for a cantilever of length L. So the table 15 and table 16 can be effectively used to arrive at L sub LT. Using this equation, we can calculate the MCR. So the ones that are highlighted in red color are the restraints at the supports, and the ones that are highlighted in blue color are the loading conditions. The point to remember is that IS 800-2007 provides the effective length of beams L sub LT based on the critical case of loading and restraint conditions. Thank you very much, and we look forward to meeting you in the next class.